Hi, welcome back. I am Rakesh Naik. Today we are going to discuss about graph coloring, which is an application of backtracking. But before we start, a small information I'd like to give. We are producing each video in two different languages, English as well as Hindi, so that you can watch each video in your preferred language. And the video can be identified from the video thumbnail. And if you have not yet subscribed, please press the subscribe button followed by the bell icon so that you can get all the updates from this channel. Please support us by liking, sharing and commenting also. Let us start graph coloring problem. The objective of graph coloring problem is, if a graph is given and we are asked to color the vertices under a condition that two adjacent vertices will not be having the same color. So this kind of problem I'll say as graph coloring problem. So graph coloring problem I can define as M coloring decision problem and M coloring optimization problem. The decision problem says whether M colors can be used to color a graph. In M coloring optimization problem, we have to say the smallest number of color that can be used to color a graph. That is called a chromatic number also. Let us start with an example. Let us say this is a graph given to us and we are given with three colors, yellow, red and blue. And we want to color this graph in such a way that no two adjacent vertices will be having same colors. Whether with these three colors, whether we can able to color the graph or not. So let us color the first one as yellow. To identify it, we will be using a state space tree, and for that vertex 1 is colored as yellow. Now in the second vertex, which is adjacent to vertex 1, I cannot give the same color yellow vertex 2, so I have given it red. The options I am having is, for vertex 2 I can give yellow, red or blue. These are the three colors, but as yellow is given in vertex 1 and it is adjacent to vertex 2, that's why I cannot give yellow in vertex 2. I can use either red or blue. Now for the next vertex, for vertex 3, I am using yellow color again. Why? Let us see. For vertex 3, again I am having these three options that I can color vertex 3 with yellow, red or blue. But I cannot use red as vertex 2 is already marked as red. So I cannot proceed by giving red color in vertex 3. I am having option yellow or blue. I have given yellow here. Now let us see the vertex 4. Can I give red? Let us check out. So for vertex 4 can be having yellow, red and blue. But as vertex 3 is yellow, I cannot give vertex 4 as yellow. So the options are red and blue. So I have opted for red first. Let us see vertex 5. Can I give blue here? For vertex 5, yellow, red and blue are the options I am having. But I cannot choose red in vertex 5 because vertex 4 and 5 are adjacent. At the same time, I cannot choose yellow also because vertex 3 and vertex 5 are adjacent. So these two conditions I have to discard. So I can proceed by coloring vertex 5 as blue. Now let us see about coloring vertex 6. So which color I can apply? I am having yellow, red and blue. So let us see. I can give yellow. Is it possible? No, because 6 is adjacent to 1 and 1 is already given yellow. Can I give red? No, because 2 is already marked as red. And can I give blue? I cannot give blue because 5 is adjacent to 6 and it is already marked as blue. Now what can I do now? Which color I have to give? In that case, what I'll do backtracking. So I'll go to my previous node, that is vertex 5. Is there any option available to me at vertex 5 except the color blue? No, I don't have any other option. So what I'll do? Again I'll go back I have colored vertex 4 as red. I am having one more option I can give. I can choose blue also. So let us choose blue instead of red at vertex 4. So for vertex 4, I am choosing blue and I am marking it as discarded or dead. So vertex 4 is given as blue. Now what about vertex 5? Now vertex 5 I can give again the same yellow, red or blue. So yellow, red or blue are marked. So which one I can give? Can I choose yellow? No, because 5 is adjacent to 3 and 3 is already marked as yellow, so I cannot choose yellow. And can I choose blue? I cannot choose blue because 5 and 4 are adjacent and 4 is already marked as blue. These two cases we are not taking, so we can mark node 5 as red. Now what about node 6? Node 6, can I choose blue? Yes. Let us see. I am having again the three options, yellow, red and blue. And node 6, can I mark it as yellow? No, because 1 and 6 are adjacent. I cannot mark node 6 as yellow. Can I mark it as red? No, because node 2 and node 5 are already marked as red and they are adjacent. So red also I cannot mark. So that's why node 6 is marked as blue. And you can see here the objective is met. All the vertices are colored and no two adjacent vertices having the same color. So this is actually the graph coloring problem by using backtracking. So here you can see for first node we have given yellow, second node we have red, third node we have given yellow, for fourth node we have given blue, for fifth node is red and for sixth node again it is blue. So this is how we are going to mark color for different vertices. Now before going to algorithm, let us see what are the different special graph and what are their chromatic numbers. Let us see a complete graph. A complete graph is an undirected graph where every vertex is having edge to every other vertex. Here you can see for vertex 1, there is an edge to vertex 2, there is an edge to vertex 3, where there is an edge to vertex 4. Like that, for every vertex to every other vertex there is an edge. What will be the minimum color that is needed to color this particular graph? This is the question. Basically, if I want to mark the first node as red, can I give it the second node as blue? Yes. I cannot mark as red because 1 and 2 are adjacent to one another. So I cannot give the same red color at node 2. Now what about node 3? Which color I can give? Can I give yellow? Yes. Because node 3 is adjacent to node 2 as well as node 1. So I cannot choose red or blue for node 3. So I have to choose some other color. And what about node 4? You can see node 4 is adjacent to 1, 2 and 3. So I cannot choose a red, blue or yellow color. So I have to choose some other color, let it be green. So for a complete graph, I am having all the vertices having different colors. So every complete graph with n vertices require n colors. So the chromatic number of a complete graph is same as the number of vertices present in that particular graph. Hope you understand this. Now let us say a bipartite graph. What is a bipartite graph? Bipartite graph is a set of graph vertices decomposed into two disjoint sets such that no two graph vertices within the same set are adjacent. Now let us say this particular graph. I am marking that vertex 1 and 2 as one set and vertex 3 and 4 as one set. Here vertex 1 and 2 are not connected or are not adjacent, neither vertex 3 and 4 are adjacent. So I can partition this graph into two disjoint subsets. So in such a case, so what will be the chromatic number? Let us see. Because these two are not adjacent, can I mark them as red? Yes, I can, because they are not adjacent. Similarly, can I mark 3 and 4 as green? Yes, I can, because these two are not adjacent. Let us see one more diagram, a star here. So is it a bipartite graph first of all? Yes, because vertex 2, 3, 4, 5, 6, they are not adjacent to one another. They can form one set of elements and vertex 1 will be one set of elements. So that's why I can put vertex 1 as a different color and vertex 2, 3, 4, 5, 6 as different color. So for every bipartite graph, I can color them with two colors only. Let us see a cyclic graph. A cyclic graph is consist of a single cycle of some number of vertices connected in a closed chain. Let us say this is a graph I am having. It is a closed chain. From wherever I start, the starting and ending vertices are same. So this is a cyclic graph. To color this particular graph, how many colors I need? Or what is the chromatic number of this particular cyclic graph? Every alternative vertices I can put colors. For a cyclic graph with 4 vertices, I can color them with 2 different colors. Alternatively, I can use. So what is the chromatic number of a cyclic graph with 5 vertices? Now you can see every alternative vertices I marked as 2 different color. Then what about this? One extra color I need, cyclic graph with odd number of vertices. So is there any formula you know? Kindly let me know in the comment section. Let us try to understand this with the help of an algorithm. So here is an algorithm, assign color to k. It means what? K is the parameter passed. The graph is represented by adjacency matrix G with 1 to n, 1 to n matrix, and xk is the color assigned to vertex k, where n is the number of colors available. Now we are going to repeat the total thing till all the vertices are covered. Repeat, generate color of k. For vertex k, I want to generate a color, and if xk equal to 0, return. It means the assignment is not possible. If xk equal to n, it means all the vertices are colored, and I have to print all the colors. And next I have to call for the next vertex k plus 1, assign color of k plus 1. So till any more vertices are left out, I have to complete this particular algorithm. Now one more algorithm is here, that is generate color of k. Here xk indicate the legal color that is assigned. If no color exists, then xk becomes 0. Then I have to do this till any colors left out. Repeat, xk equal to xk plus 1 mod m plus 1. M is the number of color that is available to me. So I am choosing my next color for xkth vertex. So if xk equal to 0, it means returns no color are remaining. Then for j equal to 1 to n, I have to find these two conditions. So what I have to do? Take care of having different vertex in adjacent by using the condition. What condition I have to use? Edge should be parent between two vertices, and adjacent vertices should not have the same color. So to meet these two conditions, I can write g of k comma j is not equal to 0 and xk is equal to xj. If this condition satisfies, then I have to go to the next color. Means I am doing break here. J will become next j value. If j equal to n plus 1, then I have to return, and I have to do this work until any more colors are left out. Now let us discuss the complexity. The upper bound on computing the time of assigned color k is an algorithm, can be arrived by noticing that the number of internal nodes in the state space tree, that is summation of I equal to n minus 1 m to the power I, and at each node order of m n time is spent by generating color k to determine the children corresponding to the legal values. So the time complexity will be big O of n m to the power n. So thank you for watching this video till the end. Keep watching, keep learning. If you like the video, kindly share and comment on this particular video. We'll again meet in one more video. Till then, take care. Have a nice time. Bye.